Okay, so hello. Today I want to go over a very extremely powerful principle called energy conservation. And I like to call this as work net, W is for work, net equals to changing K. So what do I mean by work net? Work net is all the work in a system. So you add up all the work, like work done by gravity, work done by the normal force, work done by friction, etc., 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 equals to the changing K. And, KB minus K, where KB is the final position or final velocity, right? That's the point KB. And point A is the initial position or velocity. Okay, so the question is, when do we use this extremely powerful principle, energy conservation? When do we know, actually I should state it as, how will we know when to use work net equals to changing K, or this is also known as energy conservation? When will we know when to use this? Well, anytime the problem or question asks us to connect two speeds at two locations. Should probably box this in red, right? So the only time, or like the time we know when to use this energy conservation work net equals to changing K, is when a problem asks us to connect two speeds at two locations. Okay, so let's go ahead and do an example problem. Actually, before we do that, let me talk about work first. We know by simple definitions, work equals the force times the distance. Was actually supposed to be force parallel to whatever direction times the distance. Okay, that is work. And the units for work is joules. The J is just fine for joules. Okay, so let's look at a problem, an example problem. Okay, so this problem. A block of mass m is initially at rest at the highest point of an inclined plane, which has a height of 5.82 meters and makes an angle of theta equals to 19.8 degrees with respect to the horizontal. After it has been released, it is observed to be moving at 1.04 meters per second, a distance d after the end of the inclined plane, as shown. The coefficient of kinetic friction between the block and the plane is mu p, which is 0.1, and the coefficient of friction on the horizontal surface is mu r, which is 0.2. So there's two parts to this question. A, what is the speed of the block in meters per second just after it leaves the inclined plane? After it leaves the inclined plane, this part. Okay, so from here to there, right? This point from here. And part B is to find the distance d in meters. So let's go one problem at a time. But before we go do the problem, I like to first label out the givens, the values that are given from reading the problem. So the given, right, we're given h equals to 5.82 meters. Theta equals 19.8 degrees. And it says after it has been released, right, from the top of the plane over here. Released. Released is saying initial velocity equals to 0 meters per second, right, leading it dropped or released. And the final velocity at this point equals to 1.04 meters per second. Oops, did not mean to do that. Actually, okay, I should have done this. Equals to 1.04 meters per second. Okay. And what else we have? D is not given, but we will label it. Right, that's part 2. That's where we need to find D. And then mu p is given 0.1, and the coefficient for the surface is 0.2. Right, those are our givens. The second thing I like to do before we even start the problem is drawing a free body diagram. And here's why. I'll show you in a bit. Let me first copy and paste this. Okay. So, given this mass over here, we have gravity always pointing downwards, normal force pointing perpendicular to the surface of a table or plane or whatnot, and we have a friction, right? It's going down the plane, there's a friction. And this is the friction for the plane. And then I like to draw little dotted lines. These dotted lines represents the gx, or gravity in the x direction, and the gravity in the y direction, as well with the data. Okay, hopefully that's not too blurry. I'll make that clear like this. And g dot 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 data and force friction of the plane. Okay, so reading part A again. What is the speed of the block in meters per second just after it leaves the inclined plane? So, as we can see, our target is the final velocity once the block reaches at this point from that point, right? So let's label our A and our B points. A is our initial and B is our final location, right? So A and B. Okay, so as we can see, we are given 2 locations, A and B. We are also given 2 velocity, right? Actually, one of the velocity we are trying to find. But initially, it connects 2 locations and connects 2 velocities, right? The V final, which is what we're finding, and the V initial is 0 meters per second, right? It's given. So what does this mean? This means that we can apply energy conservation. Or, as we stated earlier, work net equals changing K. Now, another question that might come in mind is, what is the work net? What is the work net? That is a great question, right? The work net is every arrow we draw in our free body diagram. That is why I said the free body diagram is very important, right? So Which arrows have we drawn? The normal force. So let's write that down. Work done by the normal force. Plus, there's the friction of the plane. So work done by friction of plane, and the work done by gravity. We drawn 3 arrows. That's it. For the gravity, there's X and Y components, but we don't need to worry about that. We just draw the main one, the main component, which is just gravity itself. So normal force, force of plane, and gravity equals to changing K. Changing K, as we said earlier, KB minus KA. Okay, and now we just need to solve this equation, right? Well, let's take a look at the equation first. The work done by normal force, that is going to equal to 0. Why? Well, as long as we have a work done perpendicular to the direction of where we are moving, then that work will be equal to 0. So in this case, the normal force pointed in this direction, right? Where is the direction that our mass is moving? The mass is moving in this direction, right? This is where mass is moving. And so that force, the normal force, is perpendicular to that direction. Therefore, work done by normal force equals to 0. You can also see over here, if I had the mass over here, right? Normal force pointing up, the direction, it continues to slide that way. It's perpendicular to the direction, so work done by normal force equals to 0. Okay, so we proved that point. And what is KB minus KA? Well, K is equal to the kinetic energy, which is 1/2 mv squared, right? But KB is 1/2 mvb squared minus 1/2 mva squared. mvb squared, vb squared is when we are at the bottom point down here, right? This is our velocity at point B. That is for KB. KA is for the top point, right? The VA is for top point. And from the given values, we already know KA will equal to 0 because the velocity at A is 0 meters per second, right? So I'm going to delete this part, but I was trying to explain why it will equal to 0. Anyway, let's continue. So now this equation simplifies to work done by the force of the plane plus work done by gravity equals to KB, which is what we wrote earlier, 1/2 mvb squared. That's easy to solve, right? We just need to solve for work done by the force of plane, the friction of the plane, plus the work done by gravity. Work done by friction. Well, remember that friction force, right? Friction of the plane, friction force equals to mu times the normal force, right? Well, in this case, for us, it's supposed to be mu p times the normal force. And since this is work, right, it is force times distance, so mu p times normal force times the distance it travels. And what is the distance it travels? Well, the distance that it will travel is this plane. So what is the length of the plane? I'll label it as x, and we'll leave it here for now. This is work done by the friction force. Okay, we will go over this part in a bit, but let's first write it down. So mu p, right, it should be negative because is going in the opposite direction of our it's going, this is our direction, but friction is pointing always the opposite direction of where we are going, right? So it'll be negative. So negative mu p times the normal force times the distance as we labeled x plus the work done by gravity. And work done by gravity is mgh, right? And it's positive. Why? Because gravity is pointing downwards and the direction of motion is also going down. So it's going the same direction, right? The gravity is going the same direction as our the direction we are moving in. So it'll be positive. So positive mgh equals to 1/2 mvb squared. Okay, so let's see what we are missing. Okay, we don't know mass, right? It's not given to us. What else? We don't know the normal force. What is normal force and what is x? Right, we don't know these things. So let's find it. So find normal force over here. Well, normal force is pointed in the y direction. And what do we know about the y direction? In the y direction, acceleration is 0, right? The block is not flying up or down, right? It's staying there because acceleration in the y direction equals to 0, right? Also, acceleration, F equals ma, so A equals to Fm, right? Force over mass, but in this case it's force net of y, because we're going the y direction, over to m. And we know acceleration y direction is 0. And what is all the forces going in the y direction? All the forces going in the y direction is the normal force and the gravity in the y direction, right? So the normal force plus the gravity going in the y direction over m. I like to put the arrows on top just so that I know it's a vector and vectors have directions. So later on, after this line, I need to make sure, is n going in positive direction or negative direction, right? Well, from our plane, we see that the normal force is going in the positive direction. So I will put a plus n. And g of y is going in the negative direction. So minus g. And what is g of y? G of y is g cosine theta. G cosine theta over m equal to 0, right? Notice that I also deleted the arrows because I put the signs. That's why I removed my arrows. Anyways, we can solve for n, right? Solving for n, you cancel m from both sides, right? M is gone, so n equals to g cosine. Wait, I realized I did something wrong. It should be mg cosine theta. So, be mg cosine theta. So that is our n. Okay, so we come back here. We know n. We need to find x. So let's find x. So, finding x. Well, as we saw earlier, right? X is over here. That is the distance of this plane. So let's go ahead and redraw that triangle. X is here. We are given h. We are given theta. And using trig, we know that sine theta is opposite in this case is h, over hypotenuse, which is x, right? So x must equal to h sine theta. That is it, right? We found x, and we have n. So we can just simply plug it back in here. So mu p times the normal force, which is what? mg cosine theta times h sine theta plus mgh equals to 1/2 mvb squared. And by looking at this equation, we notice one thing. M cancels out. Okay, let's simplify the equation. So mu p times gravity times cosine theta h sine theta plus gravity times height equals to 1/2 vb squared. Okay, well, what is our goal again? Let's remind ourselves. We're finding velocity. Well, in this case, we can just solve for the equation, right? You can plug things in right now over here and then multiply by 2 and then square root the whole thing, right? That would work. But instead of doing that, let's do it a cooler way. Let's use variables and make an equation, then plug in all the values and, get the answer. So solving this equation for VB, multiply both sides by 2. So 2 times negative mu p times gravity times cosine theta h over sine theta plus gravity times h equals to VB squared. So VB equals to the square root of 2 minus negative mu p times gravity times cosine theta h sine theta plus gravity times h. And we can now dump in our numbers. 2 times negative mu p. Mu p is again 0.1, so negative 0.1 times 9.8 times cosine our theta 19.8, so 19.8 times height 5.82 over sine theta 19.8, what we wrote earlier, plus gravity 9.8 times the height. Height is 5.82. Right. This whole thing square rooted is our VB. And, we can dump this into our calculator and see what is VB. So 2 times negative 0.1 times 9.8 times cosine 19.8 times 5.82 by sine 19.8 plus 9.8 times 5.82. And we get our velocity at point B to be 9.08. Or actually I would write it down, 9.767 meters per second. Or you can simplify, or you can round this up to 9.08 meters per second. That is it. Right. This problem for me can take up to 3 lines, but since I'm doing a tutorial, I just wrote it out even more because for better explanation. Over here, finding x, I didn't have to write it out because you can eyeball it if you are good with your trick. You can eyeball what that is. Furthermore, for finding n, I recommend writing this out. This is okay. And for work done by gravity and this, we should already know by heart. So, yeah. Anyways, that is part A. For part B, we are trying to find the distance. Target is D, right? Well, how can we find D? How can we find a d? Well, in this case, we can find d by using the same method, which is the energy conservation. Because it connects two speeds at two locations. And you may wonder, what is the two locations, right? Well, the two locations starts from point A, right? This is our new point, and B. And our two speeds is at point A and also at point B, right? A is 0 velocity. B is the final velocity, which is 1.04 meters per second. And the two distances start from 0 to D. And therefore, we can use that powerful principle. Energy conservation. So let me copy this thing again. Paste it here. And let me label A and label B, right? And we can start writing it out. W net, work net equals to changing K, where the work net is basically all the work we've drawn up there, right? So work done by normal force plus work done by gravity plus work done by friction of the plane. However, that was only for the part when we did this, the plane. But now we need to include the forces on the flat surface. So what is the forces on this thing? Gravity, normal force, friction of the surface. And what do we notice? We notice that normal force and gravity, those are two directions that are perpendicular to the direction we are going in. And remember what we said earlier? If they are perpendicular to the direction that we are moving in, those work goes to 0. Goes to 0. And so that left us with only force of the friction of the surface. So we just add work friction of the surface equals to KB minus KA, where KB starts, the KB is down here and KA is up here. And we notice one thing, right? KA goes to 0. Let me put that in a different color. So KA goes to 0. Why? Because velocity at A is 0. So if you do 1/2 mva squared, the whole thing goes to 0 because V is 0. Also over here, work of the normal force goes to 0 because it's perpendicular to the plane. We talked about that earlier. So we only have 3 works equals to KB. That's easy. Right, from earlier, work done by gravity is plus mgh. Work done by friction of the plane is not plus. It should be minus mu p times mg cosine theta. And we now need to find the work of the friction force of the surface. So remember, friction force is mu times the normal force of the surface times distance. And distance is the d we are trying to find. The d we are trying to find, right? That is what we want. Equals to 1/2 mvb squared. And as you can see, we can solve for d because we have everything given to us. Right, v is given, and we don't know what that is. We will solve for that, but we know we can write it out as an equation and dump it in this whole thing. Right. So what is n? Well, like earlier, n is in the y direction, and we know that the acceleration in the y direction equals to 0, right? And 0 equals to, what is in the y direction? the normal force plus gravity over m. It's going to be positive minus mg. So 0 equals to that. You can solve for n. Right, n equals to that. So we can rewrite our equation as mgh minus mu p times mg cosine theta minus mu r times mg times d equals to 1/2 mvb squared. And we can solve for d. Right, let's move things little by little to both sides. Right, I can move this portion over here and move this back into this equation, right? Into that side. So mgh minus mu p mg cosine theta minus 1/2 mvb squared equals to mu r mg d. Notice one thing, that is m cancels out. So let me rewrite mu p g cosine theta minus 1/2 vb squared equals to mu r g d. Divide both sides by mu r and g. So gh minus mu p times g times cosine theta minus 1/2 vb squared over mu r times g equals to d. And we can just plug in the numbers, right? So g 9.8, h is 5.82 minus the mu plane, which is 0.1, 9.8 gravity cosine theta 19.8 minus 1/2 v is 1.04 meters per second squared, all over by, what is the mu of the surface? 0.2 times gravity 9.8. So d, let's plug into the calculator and let's find out. 5.82 minus 0.1, 9.8 cosine 19.8. Okay, I realize I might have done something wrong. Okay. Good thing it's not a terrible mistake. It's not that horrible. Let me first erase this part over here. Let me actually just delete everything. Yeah. Oops. I messed up line 2 over here. Sorry. So, what did I mess up? I realized I've only done the force, but I didn't multiply by the distance, which is x. And we know from x earlier is just h over sine theta. Okay. Anyways, everything else should be the same. mgh minus mu p mg cosine theta h sine theta minus mu r times mg times d equals to 1/2 mv b squared. M cancels out. We can put the half vb squared to one side and the minus mu r gd to the other side. So gh minus mu p g cosine theta h sine theta minus 1/2 vb squared equals to mu r g d. Divide both sides by mu r g. So d equals to gh mu p g cosine theta h sine theta minus 1/2 vb squared over mu r times g. 9.8, 5.82, 0.1, 9.8, cosine of 19.8, 5.82, sine of 19.8, minus 1/2, 1.04 squared, over 0.2, let me make sure it's 0.2. Okay, good. 0.2, 9.8. If we dump this into our calculator, let's see what we get. 9.8, 5.82, minus 0.1, 9.8 times cosine 19.8, 5.82 sine 19.8 minus 1/2, 1.04 squared times 0.2 times 9.8. Our answer for our distance will be 20.74 meters. That is it. So keep in mind of this very powerful principle called energy conservation, or work net equals to changing K. This is really effective if you know when to use it. And yeah, that is it for this video. Thanks for watching.